Okay.
Oh, do I need the mic or? I don't need a mic.
I thought you had. Okay, you can have.
Loud. Okay, so thanks for the gentle introductions. I'm Karthik. I'm the co-founder and the CEO of SteamDuo. Well, the SteamDuo is a company based on Apache Pulsar, which is the next generation.
Keep the microphone up close to you.
Which is the next generation streaming/messaging system that was developed at Yahoo and running in production at large scale at several companies. Today we have the pleasure of having Matteo, who actually designed and architected Pulsar at Yahoo and put that into production, which is running at 1200 to 1500 nodes now. So Matteo, you want to raise your hands? So if you have any deep questions in Apache Pulsar, you can talk to him directly. So in a nutshell, I mean, I have a lot of slides, around 40 slides. I might go through it pretty quickly. So if you have any questions, I will try to keep it at the end because we have a small demo as well. So we can keep it at the end so that you have enough to see. So in a nutshell, if you wanted to say what Apache Pulsar is, it's nothing but a cloud-native messaging plus queuing plus compute system backed by a durable log storage. That is the simple nutshell of this thing. So now let me go through some of the definitions of what it means for cloud-native, what is messaging and what is queuing, and of course everybody understands compute. So what is cloud native? I mean, having operated a private cloud at Twitter, I used to be working at Twitter where I used to run the streaming team. So we operated streaming at over 1,000 plus nodes. So what means to be cloud native? So first is the ability to separate storage and compute layers. When you go to your EC2 instances, the first thing that you see is your EC2 is mounted back by an EBS volume, right? That EBS volume is separate from your compute instance. So you have to work under that context. So which means even your software layers has to separate from storage and compute layers. And dynamically scale the resources as and when needed. It should be instantly scalable and independently scalable. So then since a lot of people will be sharing the service simultaneously, you have to have some kind of isolation capabilities between the users in a shared environment. Then the fourth one is resource usage control. I mean, you don't want some user to run away with the system, right? So which means you need to control the resources used by the users, especially in terms of quotas and rate limiting and all the various things like that. And of course, since clouds are present in multiple data centers, you need to span, the software has to span across the multiple data centers in a seamless fashion. Now let's look at what is messaging and what we mean by messaging and queuing. So messaging essentially is a pattern by which you can, multiple different components are decoupled so that they can exchange data or do some kind of queuing capabilities between those components. So messaging and streaming is associated with what you call ordering and some kind of a stateful processing. For example, I have to process event A followed by event B because event A occurred before event B. Some kind of ordering will be there. Whereas in queuing, it is more of a paradigm of what we call like a master worker, where somebody puts some work item into a queue and anybody else can take the work item and process that, right? I mean, everybody is familiar with the JMS, RabbitMQ and ActiveMQ and a bunch of flow of systems. You can associate with some kind of a stateless processing. For example, anybody can, if a bunch of files are being uploaded into from your service, and each file has to be scanned for virus, and any worker can check for the virus and say whether certify whether that particular file is devoid of virus or it has infected with virus, right? It doesn't matter who is doing it or what order it is doing it, right? So that is the queuing semantic. So now, having operated the streaming system, we need three components in order to everything to come together. So one is the messaging, which is where the data ingestion and everything happens. Then you need storage because of the fact that the data can spill over or some late consumers can come back and pick up the data. Then also the storage is required for compute as well. I mean, the third one that you need is you have to act on the data. You have to process the data somehow to get some either some insights, or you have to do some simple data transformations or data modifications or data enrichments, all kind of various activities to do on top of the data. And once you compute the data, then you want some place to store your results as well. So you don't want to go into external systems. So you need the storage for results as well. And compute also can use storage in order to do intermediate results. So if you're trying to materialize some things, or if kind of state managements and all the various aspects require storage. So these three components have to come together in a single system in order to do your end-to-end data ingestion to all the way to data streaming. So how do we do that in Pulsar? So that will be the focus of my talk, followed by the demo. So now let us explore what is the cloud native messaging and queuing on the storage aspect of Pulsar. So just to give some idea of the terminologies, Pulsar has the notion of tenants, and the tenants in turn consist of multiple namespaces, and each namespace can have multiple topics. So for example, if you have a single Apache Pulsar cluster, you have multiple tenants in the form of one tenant called data serving, another tenant called marketing, or another tenant called product safety, who in turn will have multiple namespaces in the form of the ETL and fraud detections, and which the ETL namespace, if it's an application, then what are the topics underneath those namespaces. Now, of course, Pulsar has the notion of a topics, and it has the notion of a producer, consumer producing data into the topic and consuming data out of the topic. So each topic is further divided into partitions depending upon whether you need a partition. Unlike other systems, we don't need a lot of partitions, but if you need to partition the topic, yes, you can do it. But you can even dynamically scale up the topic, a partition topic when it's needed. Then the fundamental difference between other systems is the fact that Pulsar further divides partition into notion of segments, so multiple segments, and that gives the power of Pulsar a lot of the properties that we will discuss later in the slides. So each partition is further divided into segments, and the segments are sprayed into some kind of a storage which is underneath Pulsar broker. So Pulsar employs completely a different architecture. Like how many of you know about Snowflake? So what is the biggest advantage of Snowflake? The biggest advantage of Snowflake is the separation of storage and compute. Because the storage is nothing but S3, and the compute layer, which does all the BI capabilities and all the various aspects, are done in EC2 instances, essentially. So Pulsar also employs something on the similar lines, which is more cloud native, where the brokers are essentially stateless. It's more of a compute-like engine or a serving engine, and the bookies essentially are your storage engines. So because of this two-layer architecture, it allows you to have independent scalability. You can scale the brokers whenever you want to, or you can scale the bookies whenever you want to. It can be independent, and also you can scale them instantly. And when you run that under the context of schedulers like Kubernetes, it's just a one single command. Just scale brokers, set the replicas from 6 to 8, boom, just the pods will just multiply. So now, Pulsar has this notion of, I talked about the segments, and the segments are stored in the underlying in the bookies, and the segments are replicated and stored on the individual bookie nodes. And whenever some bookie node dies, this current segment is closed and the new segments are open. And there is no type ownership between the segments of a particular partition to a set of storage nodes. So one segment of a particular partition might be on bookie 1, 2, and 3. The following segment could be on 2, 3, and 4. So depending upon what system at any given point is available, that will keep continuously writing it. Because of that, the write availability of the system is very high. In the sense, like, as long as if you have k replicas of segments, as long as any k nodes are available in the system, it can continuously write. For example, if you are having a replica of 3 nodes or 3 copies, any 3 nodes is available. I don't need to do the particular 3 node. So now let's look at broker failure. So whenever the broker fails, so all the topics that are owned by the broker or the partition is shifted in ownership, and again all these things occur dynamically. Then the state of that particular partition or broker can be reconstructed very easily, because the data is already only on bookies, right? And meanwhile, the brokers are exchanging continuously some kind of load information that allows whether some brokers are loaded or not. If they are loaded, then automatically the load is shifted from the highly loaded broker to the leastly loaded broker. So there is no copying of data or any kind of things. So failover is handled transparently by the client library. So What it means is if a client or a producer or a consumer is connected to a particular broker and the broker is died, and automatically the client connection will take care of reconnecting to the appropriate broker which has the ownership of the same topic that it was publishing to. Now let's look at the bookie failure, which is essentially the storage failures, right? So if a current segment is being returned at the time if it breaks down, so that the current segment is closed, and kind of there is something called fencing protocol is run very quickly to close the segment and identify what is the least amount of copies that you has been maintained, and the portions that are not being returned will be re-returned into a new segment which is opened on a new set of nodes, and it keeps writing. So which means there is no tying of a particular partitions topic to a particular set of nodes. Instead, it can be fluidly can move around between these bookies as long as any bookies are available. Sometimes if you feel that a bookie is like a 70% or 80% full, I want to convert that into a read-only bookie. Automatically you can do that by setting a configuration, or you can set a configuration element by sending some command. So it makes the bookie read-only, so which means the bookie will automatically turn read-only, so the writes will automatically shift without having to do anything. You can do all of them in production. Then again, as I mentioned, as long as any 3 bookies are available in the cluster, we can continue to write. So which means the write availability of the system is high. So now, one of the thing is if one of the bookie node goes down, so what happens? Because you have the lost replica count of the segments on the bookie by reduced by 1, right? So in the background, we have the notion of what you call bookie recovery process that brings back the replica count to the whatever the desired value by using what you call a many-to-many recovery process. And the reason why it is a many-to-many recovery process is because the segments are distributed across multiple nodes, right? So if segment 4 and segment 1 are asked to be recovered, segment 1 can be grabbed from bookie 1, whereas segment 4 can be grabbed from bookie 4. So which means I'm effectively using the disk bandwidth of multiple different systems in order to recover the replica count. So which means the recovery will be much faster. And because of not only because the disk, but also the network. Because of the network is on point-to-point on a switch, right? You get the full bandwidth of the network as well, so that the recovery is pretty fast. So in addition to that, if you wanted to expand the cluster, all you have to do is just add nodes. Either you can scale up the brokers or bookies, and then the percentage of writes will start shifting into the new set of bookies, and the new segments will start filling into the new bookies without having to take down the cluster or wait for rebalancing, wait for all these other mundane tasks. So in addition to that, Pulsar also implements something called tiered storage. In the sense like when the segments are older than a certain amount, you can transparently move the segments from bookie nodes to something like cloud native storage, like low cost storage like AS3, on an on-prem kind of environment like Mini.io or Hadoop or whatever it is, right? So those segments can be transparently propagated, and these segments, what we do is we just copy the segments and we update the metadata of the segments. Rather than pointing to the segments within the bookie, it points to the buckets or whatever might be the low-cost storage means. So just to swizzle the metadata after copying the data. And we are working on some aspects of where when the segment is being returned into low-cost storage, we can write it in something like a Parquet format and all these various stuff, so that any analytics workload, if you wanted to hit like Presto or Spark, if they want to hit those, they can directly go to the storage nodes rather than going through the various, going to across a different system and do it, because of the fact we can infinitely store the data as long as you want. So like, what are the differences? Like monolithic systems like Hadoop and Kafka and all these things are try to be where each partition is stored in a particular broker, where the storage and the serving are combined together. So because of the fact it is a partition centric, it's cumbersome to scale, which means it requires rebalancing and moving data around. Whereas in Pulsar, like because of the fact the partition is further divided into segments and the segments are spread across multiple nodes, it's completely decoupled and it's flexible and easy to scale. This is the fundamental difference between systems like Kafka, RabbitMQ, Hadoop, and all the various things with respect to Pulsar. And that's why Pulsar is more cloud native than other systems. So Pulsar also provides more durability and consistency, in the sense like by default, Pulsar always produces data. The data, when it's being replicated, it always uses the fsync. And the reason why we do fsync is we do the notion of a journal versus logs. Sorry, the data area, like similar to regular database systems. Right ahead. How many of you have heard about write ahead logs for transaction recovery and all the various stuff like that, right? So we have the notion of a write ahead log, and the write ahead log is where the data gets flushed out. The moment that data is fsynced into a disk, immediately an acknowledgement comes in. So not only the data is replicated, it's also fsynced across multiple systems before an acknowledgement is given to the producer. By the time an acknowledgement comes to the producer, the data is fsynced on multiple replicas as well as consistent. So because of that, it provides a highly durable property, like in the presence of rack failure or multi-rack failures, you can survive those. So the next model, like as I was mentioning, Pulsar was originated when a bunch of systems were islands of systems were there in Yahoo. Like there were systems for RabbitMQ, JMS, and there were systems like Kafka, ActiveMQ, and other things. So what we did is, instead of having islands of systems, they want to consolidate all the semantics of multiple different systems into one single system. So underlying, like it happens to be two different semantics. One is the messaging semantics, another one is the queuing semantics. So Pulsar tries to address those two semantics by doing something called subscriptions. Like it's very similar to Kafka, consumer group in Kafka, right? So these subscriptions, there are multiple different subscriptions, and based on the type of subscription, you can get the different semantics. So one is called exclusive subscription, which means you consume out of a topic or a partition of a topic, and if any other consumer tries to connect to that, it will disconnect, in the sense like it's exclusive. Only one person can do. If you wanted to have a what you call a failover, you can declare the subscription to be a failover subscription. So at any given point, only one consumer will be consuming out of that partition or a topic, but any other consumer will be standby. The moment the consumer one fails, all the unacknowledged messages will be replayed in the same order to the standby consumer, which was become primary at that point. So it will automatically cut over. So the queuing semantics is provided by what we call as a shared subscription. So the shared subscription, the data is given to the consumer, whoever wants it quickly. So in the case of consumer 3, it is getting M0, whereas consumer 2 is getting M1, and consumer 1 is getting M2. So it's round robins, but if some consumer is processing the data much faster than the other ones, the data will be given to them very quickly. So because of that, you have to selectively track which has been processed and which has been not processed. So Pulsar has the notion of individual acknowledgement for each of the message, and it also tracks those individual artifacts. For example, M4, M0, M3, M6, M7 might be processed, whereas M4 is still in the process of getting even crunched out, right? So that time, like it will keep the acknowledgements for M6 and other things has been done. So which means if M4 consumer processing is going down, only M4 will be delivered to the new consumer. So that way you can keep track of millions of messages from an ACT perspective. So then, as I said, like another capability for the cloud native messaging or /streaming system is how to seamlessly work across data centers. So Pulsar has the inbuilt disaster replication and recovery completely, like where you can do active standby, where data is published in one data center and it's consumed on a different data center, or you can do vice versa, and you can do multi-directional, like currently, like largest production runs on 8x8, in the sense like data coming from one data center is replicated to 8 or 7 other data centers, and you have producers and consumers on across both of them. So so the key thing is like it's all inbuilt into Pulsar. There's no need to run a separate replicator or a mirror maker or an orchestrator. It's part of the broker code itself, and it's all integrated in the message workflow. And you can easily add a new region. If you want to add a new region into the data recovery, you can add the data center T also, then make sure everybody knows about it, then automatically data gets replicated. You can even selectively say what is the namespace that you want to replicate, what is the tenant that you want to replicate, then you can replicate that one as well, rather than replicating everybody. So you can even do synchronous and asynchronous applications. I'll show in the next couple of slides. So this is the synchronous applications. So you have a primary, you have a secondary. So one data center is primarily active where the data is being produced, and the data is being continuously asynchronously replicated. But the producers and consumers are not running at that point. So when a data center goes down, the primary data center goes down, data is still available. Now you can start the producer and consumer. Now when you start the producer and consumer, the same producer consumer where in the primary data center died, so how to pick up where it left off? That is where something called a replicated subscription that we delivered on 2.4 Pulsar, where the subscription that we do, the exclusive failover and the shared subscription, it keeps track of the state of every consumer where at the particular message, which message was last consumed, what was not last consumed, right? So that state is replicated across the geo data centers. So when the consumer comes back on the standby data center and tell that this is the same consumer I was at the primary, it will replay from that point where it close it was, because there's a small delay between asynchronous. You'll start not exactly where it left off, but very close to where it left off. So that is what we call asynchronous application with replicated subscriptions. Now, if you in a financial kind of environment like banks, you want exactly where you left off. So in this case, you can have a single Pulsar cluster that spans across multiple data centers. So which means whenever you publish the data, a copy of the data will be committed to multiple data centers simultaneously before acknowledgement comes through. So which means like when the producer cut over to the next data center, because the primary data center is down, he will exactly pick up where it left off. So which means this is good for like more financial relation application where duplicate processing is not desired. So you can use the same things to edge to core in the kind of IoT like environment, where you can have an edge Pulsar cluster, which is a single node Pulsar cluster, and that can point to primary and standby. It can continuously replicate data, moving data around in all kind of contexts. So Pulsar also provides multi-tenancy. Because Pulsar is designed to be a cloud native system, and people who use Pulsar operate that as a cloud service internally. Internally within the organization. So internally, one organization will be responsible for one single Pulsar cluster that they want to manage, and all the teams are onboarded onto the Pulsar cluster. So as I said, like here we have multiple tenants, and because of the fact it's multi-tenant, its authentication is inbuilt, and already it ships with Kerberos integration, auth integration, and TLS integration. And it also provides authorization plugin if you wanted to connect to your authorization plugin. Data is encrypted and decrypted, encrypted the rest also, and decrypted only in terms of processing, only you have the keys. And you have the notion of software isolation. So you have storage quotas. You can say particular application cannot take more than 1 terabyte. So you can control the storage quotas, as well as you can control limit how fast you can publish data into that particular namespace or topic. So you can control all these various elements so that some team is not running away with the resources in the cluster. In addition to that, if there are critical tenants for which you want to have a complete isolation, you can even tag certain nodes. Okay, this is designated for this team. So you can even isolate the storage, isolate the brokers for that team, but still as part of a single cluster. So that is the notion of multi-tenancy. So this is essentially the quotas at different levels that you can set. So now we have seen the various aspects of Pulsar from a cloud native perspective, as well as from the perspective of messaging, queuing, and other aspects. I didn't go too much detail into it, but it's just a high level at this point. If you want more details, you can dig into the documentation. There's a bunch of other features that are available. So now let me talk about some of the compute aspects of Pulsar. So there are, based on our experience, we modeled the compute into four different types. One is consume the data as it's produced. That is one type of compute. In consumer, you do whatever you want to. Then we further divided the compute into heavyweight compute and lightweight compute. The heavyweight compute is more on the style of continuous DAG processing, like Spark streaming, Flink streaming, K-streams, and all the various things. These are all more DAG-like processing, where you express everything in more in a DAG. And then there is the notion of lightweight compute, So where you would do more in the form of lightweight, like lambda file like functions. Like you transform data and React, and you just do only one stage computation. And after that, there is, since the data is stored in the cookies for a long term, you might want to interactively query the data. So that's what we call as an interactive query of stored streams. Because the streams are stored in infinite retention, you want to slice and dice the stream based on time or different other dimensions. So like, what are the lessons learned? I mean, having operated streaming for quite a while, our experiences taught us like most of people do very simple tasks in streaming. One is data transformation, data classification, data enrichment, data routing, data extraction and loading, real-time aggregation, and simple microservices. So significant set of 80 or 90% of these tasks are exceedingly simple. So in order to do simple things, do we have to learn Scala, functional programming, DAGs, and all the various things? Probably not. That's why we decided we have to do something about it, and we invented something called a lightweight compute, where it's nothing but a function. So you have the incoming messages from topics, either one topic or multiple topics, and the function essentially acts on those data elements, then outputs those messages into an output topic. So the simplest possible API, which is nothing but a Java function or a Python function, you just write a function, just compile it and deploy it. Automatically Pulsar will take care of the rest of the stuff. And support for multi-language. Today we support Java, then Python, and Go. And it uses the native API for each language. You don't have to learn special APIs. And it also scales developers. If you know one language, any programmer can program it without having to learn any new things. And it also uses the same messaging first native concept. It doesn't introduce new concepts like input, output. The function input are nothing but input topics. Function output is nothing but an output topic. So very naturally it flows. So it can be run as a simple standalone applications, or it can be managed system applications where you can run it in a broker or outside broker, or even run in Kubernetes. So if you look at a simple Pulsar function, it's nothing but just to apply the string input. Input is nothing but it will be bound to a particular topic. When you launch the function, you say my input for this function is nothing but this input topic. Now when the output topic also is indicated, including the function submission, so then automatically when the function executes, it will just pick up the data from the input topic and convert that into a string and add an exclamation into this and put it to the output topic. So it provides all the semantics guarantees, like at least once, at most once, and effectively once. It can be controlled with the runtime, so you can change your particular function from at least once to at most once with the change of the command line, or a simple configuration change.
Sorry, what's effectively once?
Effectively once is loosely called exactly once, but we don't call exactly once because exactly once is never achievable. So deploying functions, you can deploy in the same node where the broker is running, and sometimes that might not be desirable because you are eating into the resources of the broker, because brokers are critical for your functioning of the system. So which means you can run those functions in separate systems where the workers are sharing the nodes and orchestrate it. If one of the nodes goes down, automatically it will orchestrate to some other nodes. Or you can run it on Kubernetes as well, so where everything is running in terms of pods. So brokers are runs on pods as well as each function instances will run as pods as well. Then finally, like how do you do the interactive querying of streams? So like remember we have the two-layer architecture where you have the notion of brokers and you have the notion of bookies. And in the bookies, like we have this notion of a segment reader. So because bookies are mostly getting writes, they're never used for reads. Only when the broker goes down and comes back in a different node, it will bootstrap some state from the bookies, right? Other than that, is hardly used for reads. So the read bandwidth of the disk is never used, and also the read outgoing network bytes of the bookie nodes also not used. So instead, like we have the notion of segment readers, which allows you to read those segments which are located on these bookies, and whenever you issue the query, those query is segmented like into the shards of where the segments are, and the queries are running on those shards corresponding to the query. So, for example, let's say you want to query the topic 1, and the topic 1 segments are distributed across several nodes. Now, because of the fact it's distributed on several nodes, the metadata will indicate which segments are placed in what nodes, and based on that, so the segment reader for those nodes will be activated, and they will read the appropriate segments and process that portion of the query on the chart, and then like an MPPB style system. So internally, what we did is, I think, but we integrated Presto, the query engine into Pulsar, so that we have the bookie readers, and the bookie readers essentially get the data into Pulsar, into Presto, which in turn computes the results and gives back. So companies using and contributing to Pulsar, there's a bunch of them, ranging from Verizon Media, which is the Yahoo, GM, Comcast, Toyota, Nutanix, and a bunch of companies. So far, we have been counting around 300 plus companies so far using in some form or other. So Pulsar as a SaaS, how do you deploy it? I mean, one of the key thing is, because Pulsar is a cloud native, if you want to deploy it in your organization as a either as a cloud, which is running on AWS by yourself, or you might want to do it on a private cloud. So it requires some additional components, like one thing that we have added is something called proxy layer. So proxy layer, especially if you're running on Kubernetes cluster, because you don't want to get the data, expose the broker IPs to the outside world, because they will not be valid, because Kubernetes load balancer is Kubernetes IP addresses are on an island of its own. It has its own networking. That IP addresses are not validated outside. So instead, you use the proxies and expose the proxies through the load balancer. And also, like, you need a metrics, like Prometheus, like a system, in order to get all the metrics to identify all the metrics about how brokers are doing, how the bookies are doing, how the proxies are doing. And of course, you need the UI, so which Jerry will give a demo about. And all the capabilities of producer, consumers, and all admin everything goes through a single load balancer. So if today we are announcing the Apache Pulsar as a SaaS preview. If you're really interested in, you can try it out at this URL. It's in preview mode. We are testing it out, a bunch of things. It's a multi-tenant shared system. Each user gets logged in, gets a tenant, and within which you will have a namespace and 10 topics and a few sources and things and functions that you can deploy it and try it out. So now I'm going to hand it off to Jerry, who has been working on some demos that he wants to demonstrate. So you will demonstrate the sentiment analysis if you want to do it in Pulsar, how we can do that end-to-end in Pulsar. Jerry, you want to take over?
Hi everyone, I'm Jerry from Streamwheel, and I'll give you a quick demo of our preview of our Streamwheel Cloud, which is our SaaS offering of Apache Pulsar. And through this demo, and our CP of Apache our cloud, I also want to show you how Apache Pulsar is truly a cloud-native platform. So this is kind of the first page a user gets to when he or she logs in to our SaaS offering of Apache Pulsar. This page kind of gives you an overview of everything the user owns, the resources the user owns in our SaaS offering. So as Karthik mentioned before, Apache Pulsar is truly multi-tenant. Things are organized under tenant, which is currently me. And then namespaces and topics, functions, sources, and sinks are basically organized under tenant and namespaces. So for example, this is what I'm running currently in our SaaS service. I have some topics, functions, and connectors.
I don't think the
running.
microphone's on.
Not on? Hello? Can everybody hear me? Is it better?
Now we can.
Okay, let me keep it really close to my mouth then. So I can, since I'm an admin, I can switch to, let's go look at what Karthik is doing, right? It's truly multi-tenant. He has some stuff running. If I'm just a normal user, I wouldn't know what he's doing and he wouldn't know what I'm doing, but basically, we have all this stuff is built into Apache Pulsar to basically keep users separate and truly have this multi-tenant experience. And you guys see this UI, but all these features are available in open source as well. We have a nice, beautiful UI to increase the user experience, but you can also just do this through the command line, if we're interacting with Pulsar as well. So as Karthik mentioned before, originally, Pulsar was a messaging system, but Pulsar has evolved in a way that it has far more capabilities of just producing and consuming messages. You can orchestrate whole data pipelines within Pulsar itself. So just for let's do an example. Go through an example to kind of demonstrate the Pulsar as well as our cloud service. Let's create basically a pipeline that does sentiment analysis on tweets. I don't know if you guys remember the kind of the brief figure that was one of the last slides of Karthik. It showed kind of the full pipeline of the sentiment analysis, but I'm not sure I can share Karthik's screen, so I'll just describe it. So what we're going to do here is basically create a source, an ingest of tweets from Twitter, and then I'm also going to create a Pulsar function that performs a sentiment analysis, and we're going to classify tweets as positive, neutral, or negative, and then we're going to reroute those tweets into 3 separate topics based on their sentiment. And last, we're going to use Pulsar SQL to kind of look at the results. So how to do that in basically Streamable Cloud is super simple. I can go and create a Twitter source. Just call it Twitter. Let's say we output to our tweets topic. Click next. Let me type in all my very secret passwords for Twitter Firehose. Sorry. A second here. So, yeah, I mean, feel free to share them. I'm going to delete them later anyway, so whatever.
So we should use them now.
Exactly. And I mean, it's a public API anyways. You just get random tweets. So I've created basically this Twitter source. I also have this data generator source running just for a test. But I've created this Twitter source. We can go take a look. It's running. I've already got 29 tweets, 29 messages, so on and so forth. So next, let's create our sentiment analysis function. I already have a function running here as a test. It's written in Python. But sentiment analysis function is written in Java. So give me a second here. Already typed this through. Can just add the topic, which is our tweets topic. Add it. We'll have any output. Last name. One. Resources. Then I'm not choosing a file. I'm just gonna there was supposed to be a link for uploading your package using a URL, but that is not there yet, so I'm just going to upload it with a file. But this could take a little longer. Sorry, give me 1 second here. Demos, right? The very things unexpected happen. So I can also upload it. and then I can create this function. Oh man, this is tough. What's going on, guys? Well, obviously something went wrong, but we're actively improving our UI. But just for example, just assume we've created this function, right? Maybe listed here as well. But I've already created this function before, and there's already some tweet data that we can query. We can query the data just by using Pulsar SQL. So for example, so we can query the tweet topic that I have some data in, and I can just run it, and it returns the results here. Sorry, it's really small to see, but we have not close to 9,000 tweets. And just to reiterate what Karthik said about Pulsar SQL, we can query both new data and historic data. So new data arriving in, we can query that as well as data that's offloaded to S3 or some other object store. We can basically query all of that data within one framework. So in terms of this is the number of tweets we have, but in terms of sentiment analysis, we can say have a fun SQL query to see what people are tweeting about a president, just for the heck of it. We can run it, what people say about Trump on Twitter, see what happens. Results varied, I guess.
Could you clarify what is the source?
Sorry?
What is the source?
What is the source?
Yeah, it's like another application.
Yeah, so the source is so we're basically, the pipeline is where we have a Twitter source, right? That's reading data in from Twitter, and then we have our sentiment.
What is it like physically? Like, is it like a Java application?
Yeah, so physically these things are built in, right? And this is also a feature in open source as well. We have in Pulsar, we have a lot of built-in connectors that basically is just packaged with the binary distribution. But you can also write a custom source. Basically, it's basically a Java application that's run by the cluster. And just a side note, Java sources and sinks, our connector framework, as well as our functions, they're basically run by our cluster in the cluster as well. So the user really don't need to figure out how to or where to run their application or sources and sinks in a reliable fashion. So things like running and scaling, those are things that are already taken care of by the cluster, and that's not just in Streamable Cloud. That's also in open source as well.
Is it like Kafka Connect on server side?
Yes, I mean it's similar. It's similar. We have sources and sinks. I'm not too familiar with the Kafka Connect framework, but it's a connector framework that's basically run by the. But we can also scale out. So all the function, there's quite a few capabilities of Pulsar functions, and all of them are shared also in basically our connector framework as well, such as state processing. So offsets you have, or whatever data you need to store for your external connector, you can store them in basically function state, which is for stateful processing within functions as well.
Thanks.
Yep. So and we have distributed counters. I mean, if anyone cares, distributed counting used to be a really hard problem, especially at scale. But since we have, we built in distributed counters, you can easily just increment a key within your function, and basically and basically all of the aggregates will be aggregated for you, and you can query those aggregates anytime after basically you submitted that function. So that makes distributed counting, which used to be a hard problem, very easy. So kind of going back to our query here, we got some results. Seems like, I don't know, not too many negative tweets about it, I guess, some positive ones and a bunch of neutral ones. So that's kind of a demonstration of Pulsar SQL. You can query all of the data. We're good to go. Should we try to submit the function again? I don't know. We can see. We can go back to functions. We can see what we created. Oh, now this is here. Okay, so just to demonstrate, right, to make it concrete, we can do this again. And then the URL. This is our sentiment analysis, and then our class, and then number 2. Okay, let's create it. It's I mean, because it contains a model, it does take a couple seconds to run. It's but it should return pretty fast here. Yep. So it's created. Here it's in Java. You can take a look. It's not yet up and running, but I went through the rest of the demo, so the gist of it is it performs the sentiment analysis and reroutes the tweets based on sentiment. But what is also interesting, I guess we can kind of show another feature that makes Pulsar and Pulsar functions really cloud native is the scaling part, right? So I have this function already here that basically it's a Python function, and kind of just to give you a brief. Oh, give me 1 second here. Well, I was going to show you a really simple Python function and how to write it, but I can't seem to be sharing my other screen. Maybe here, share. I'll try again. Sorry, give me 1 second here. Oh, but it's not showing up, right? Okay, whatever. I can just come back to it. Still not showing. Oh, sorry. Yeah, thought it was not showing. So we have a Python function that's running, basically reading out from a data generator source. There's a backlog growing currently. So what we can do when there's a backlog, which means that our rate in is higher than our rate out, we can easily just basically scale our function. We can, current parallelism is 4. But we can, increase that, and even CPU, we can just update our function. It gets updated, we can go back to it. And as you can see, it starts running, and well, it's when it restarts, it's going to start going down. As you can see, it starts because we increase the parallelism. Now the function has more processing power. So it can basically process messages at a higher rate. So thus we see basically eventually the backlog will start clearing. So that's all I had for the viewing of basically our demo of our Streamliner cloud interface. A lot of everything I've demoed here, you can do this in open source just through a command line interface. We just Streamliner will make the experience a lot easier for you by having basically this pretty interface for you to use. So just to kind of give a brief overview of this is not a user-targeted UI. This is basically how we're running our cloud servers internally. This is a Grafana dashboard that's monitoring basically our infrastructure that our SREs and our admins would use. So this kind of shows we have a really small demo cluster we have running here. 3 bookies, which is a storage layer, 3 brokers, and so on and so forth. But I want to really make the point solid here that it's really easy for admins and our SREs to operate our cluster. If there's, we need more storage, we can just increase the number of bookies while everything else is running. All our user production workloads would be running as normal. Or if we need more CPU, more CPUs for functions or serving, we can just increase the number of brokers to adjust them, accordingly, right? Which makes really, an easy experience to operate Pulsar on the cloud, especially, when Karthik defined cloud as, being this elastic, place where you can dynamically scale in and scale out, right? Which Pulsar is really the platform to do that. And that's all I really had for the demo. I mean, Karthik, if you want to come up, and if there are any questions, we can take some questions. Thank you.
Okay, wait for the mic.
I thought it was the presentation is really nice. Has simplifying all the aspects of data pipelines. is there sort of like security in mind when you're defining topics, like topic level security and like having separation of concerns built into Pulsar and sometime in the future, or what's the sort of current state that you have in mind?
Yeah, there's a bunch of security levels that you can configure. So Pulsar is, as I said, like authentication is built in, authorization is built in, encryption also is built in, and you can do encryption based on signing up. So it means Pulsar won't even see the data because it's encrypted at the user level itself. And whoever has the principal security, they only can decrypt it and then distribute it, right? So even if I can see the data on the topic, I won't be able to decode what is the data. So it has all the mechanisms in place. So it's all again open source. Extensive as it is, and you get all right out of it.
So a lot of the separation of the compute and storage when it's done in like multiple databases and the partitioning of the load balancing that you talked about is already like done in multiple databases. So is your USP sort of applying that to the stream processing environment and marrying the compute at the top and sort of the separation?
So
He has a mic.
Currently the brokers and everybody load balances themselves because moving the ownership of the topics moves between brokers depending upon which one is likely loaded and which one is overloaded. Now the same thing can be applied to functions also. Like for example, how to scale up the functions and scale down the functions automatically. It's a pretty simple problem, but we are not done it yet because there are some kinks into that because just merely scaling when the backlog is increasing is not the right model to do because you have to look at the function as a black box. Why the function is not going faster, right? Because you've been given enough resources, right? So there are three possibilities. One is the function is not going faster because the input data versus provisioned resources for function is not right. Second one is the function got scheduled unfortunately in a slow mode, right? Third one is if the function is doing some external calls depending upon some other services, then if that service is going slow, just scaling up the function is not going to do anything, right? So that's why these multiple things you have to take into account before you can scale it up. When is a true scale up, when is a true scale down that you have to do, right? So we know we have published a paper under the context of RM called Dalian, self-governing streaming system or self-regulating streaming systems. We will take some of those concepts and apply here, but we have not done it yet.
And then for a word about Zookeeper, because at scale, like Zookeeper at scale, as you can have like performance problems.
No. In fact, the Zookeeper is very minimally used in Pulsar actually, because a lot of the data, metadata, and everything is stored in Zookeeper itself.
Yeah.
The Zookeeper stores only metadata.
Zookeeper is only really used for coordination, like a lot of blocks, leader election, that's used in Zookeeper, but a lot of the heavyweight metadata, that's already stored in Bookkeeper, which is a storage layer as well. So we basically try to minimize the use of Zookeeper. That's why we can scale out our topics to the millions. And how many topics are there at Yahoo, Mateo? Like 2.5 million topics. So, we don't, Zookeeper doesn't scale, right? We know that, but we don't really store that much heavyweight stuff on Zookeeper.
So that's a single cluster.
Next question here.
Yeah, can you talk about the replication story? Because a lot of times messaging queue is used for one, ordering two is replication, right? Basically the write-ahead log of a lot of databases. So how do you handle the replication story? For example, when you write from a broker to, let's say, a bookies, and let's say if it has 3 copies, what kind of guarantees are you providing?
So you can configure that is the right quorum, right? So you can say 3 out of 3, so which means all the 3 has to be synced before acknowledgement comes in, or you can do 2 out of 3. So that is a configurable element that you want, depending upon what consistency levels you want, you can configure that.
So then, how do you maintain? Like, do you guarantee like all the same segment in all the 3 hosts are going to be the same? Because if you do 2 out of 3, then one of the segments is going to be different, right?
Yeah, but the one is going to be one is going to be replicated.
It's a long subject, so
Yeah.
it will be like a half an hour answer. But I think in the Bookkeeper client can take consistency and make sure that if you do 2 out of 3, it will repair the third replica. It will switch to a new node and write the third copy there, and make sure that the metadata is updated, so such that it knows that entries from 0 to 9 are in book 1, 2, and 3, and entries from 10 on are in 2, 3, and 4.
I see.
Okay, last question, if any. All right, no more questions. Thank you so
Thank
much.
you.
Give me a second, change the battery.